Today we're going to look at section 10.1, which is on linear regression. So when we're comparing two different variables, a few questions come to mind. Is there a relationship between these two variables? What is the nature or shape of the relationship if so? And how strong is that relationship? These questions can be answered using regression and correlation. Regression is going to answer whether there is a relationship. We're only going to be exploring linear relationships. And correlation is going to answer how strong that relationship is. Remember that our independent variable or explanatory variable or predictor variable is going to be the x value, and our dependent variable or response variable is going to be our y value. So we're just going to go ahead and look at some data. Is there a relationship between the alcohol content and the number of calories in a 12-ounce beer? To determine if there is one, a random sample was taken of a beer's alcohol content and calories, and the data is presented in this table. To help us figure out if there is a relationship, we could draw a scatter plot of this data, plotting the alcohol content on the x-axis and the calories on the y-axis. This is because it would make the most sense to assume that if there is a relationship, that the alcohol content here is the independent variable and that the calorie count is the dependent variable, that the calorie count would depend on the alcohol content. It wouldn't make too much sense to think that the alcohol content depends on the calorie count. And once we have a scatter plot, to find the equation for the linear relationship, we use this process of regression. The process is to draw a line through the data and then find the distances from each of the points to the line, which are called the residuals. The regression line is the line that makes the square of the residuals as small as possible. So the regression line is also sometimes called the least squares line as a result. The regression line and the residuals are displayed here in this graph. There is a process of calculating the regression equation by hand. However, this process is pretty complicated and pretty time consuming. So we're not going to do this by hand. We're just going to look at how to do this in a calculator. Our population equation is going to look like y hat is equal to beta naught plus beta 1x, where beta naught here is the slope and beta 1 is the y-intercept. Here, y hat is going to be used to predict y. The assumptions of our regression line are that the set of ordered pairs xy is a random sample from the population of all such ordered pairs. And for each fixed value of x, the y values have a normal distribution. All of the y values have the same variance, and for a given x value, the distribution of the y values has a mean that lies on the least squares line. You also assume that for each fixed y, each x has its own normal distribution. This is difficult to figure out, so we can use the following to determine if you have a normal distribution. You look to see if the scatter plot has a linear pattern, and you examine the residuals to see if there is randomness in the residuals. If there is a pattern in the residuals, you actually have an issue. You want for your residuals to be kind of randomly distributed. So we're going to look at how to answer the question that we posed earlier in a calculator. This question of, is there a positive relationship? We're going to be asking, is there a positive relationship between the alcohol content and the number of calories in a 12-ounce beer? I'm going to input in my calculator all of the data that we had in our table earlier. In L1, I'll be typing in the alcohol content. And in L2, I will be inputting the number of calories. And now we want to use, as you see on the screen, this thing called lin/reg t-test. So I want to now go to stat, tests, and all the way towards the bottom of tests, there is lin/reg t-test. We want for our X list to be L1 and our Y list to be L2 in this case, and they're already set up this way. We don't change this frequency thing. And down here, we want to choose greater than 0 because the question asked if there was a positive relationship. Right now, this choice isn't actually going to make a difference for what we want, but it will be important later. Then we go down and we hit calculate. And now here, the A that you have is the y-intercept. We can scroll down. We can get that this B is the slope. So we can interpret the calculator output here as telling us that the equation of this regression line is y hat is equal to 26.3 times x plus 25. If we are asked to use our regression equation to find the number of calories when the alcohol content is 6.5%, we would just plug 6.5 into our equation, and we would get 196 calories. So if you're drinking a beer that is a 6.5% alcohol content, then it's probably close to 196 calories. Notice that the mean value, the mean number of calories is 170. This value of 196 seems like a better estimate than the mean, when looking at the original data. The regression equation is a better estimate than just the mean in this case. This is an example of interpolation. We call this interpolation because the value that we are predicting uses an x value that is within the range of the original x values. So our x values go from 4.7 all the way up to 8.1, and 6.5 is within that range. But now if we want to use the regression equation to find the number of calories when the alcohol content is 2%, when we plug 2 in to this equation, we get 78 calories. Now, this estimate is what is called extrapolation. This x value is outside of the range of x values that are in our original data. So this could potentially be a bad prediction. We want to typically avoid extrapolation as a result. We want to avoid predicting for x values that are far outside of our original data, because we can never be sure that this regression equation is valid for data that is outside of the available sample data. When we plot the residuals for this data, they look like this. You can see that there doesn't really appear to be any kind of pattern going on with these residuals. The sum of the residuals is 0 by design, but it may not look like that due to rounding. And again, if there is a non-random pattern to a residual plot, this is a tip-off that the relationship may not be linear. Remember that the slope is the rate of change of the dependent variable compared to the independent variable. In this case, it's the number of calories that you expect to add every time you add 1% to the alcohol content. So we would say that the calories increase by 26.3 for every 1% increase in the alcohol content. The intercept is what you'd expect to get for the y variable if x is 0. 0 is far outside of the range of our data, which would be extrapolation. So that isn't going to be meaningful in this example. The p-value that we get for our calculator readout, let me once again do the linreg t-test. Oh, choosing greater than 0 and calculate. The p-value that we get here, this 2.88 times 10 to the negative fourth, means that there's no if there was no real relationship between the independent and dependent variable at all, the chance of getting a random sample that looks this much like a line is very, very small. And one more example of the dangers of extrapolation. So an example of extrapolation is when you use regression to come up with an equation to predict the growth of a city, like Flagstaff, Arizona. Based on analysis, it was determined that the population of Flagstaff would be well over 50,000 by 1995. However, when a census was undertaken in 1995, the population was less than 50,000. This is because they extrapolated and the growth factor they were using had obviously changed from the early 1990s. And growth factors can change for many reasons. Things like employment growth, employment stagnation, disease, articles stating that this place is a great place to live, or maybe this place is like an awful place to live, etc. Realize that when you extrapolate, your predicted value may not be anywhere close to the actual value that you observe.